Hey guys, and welcome back to the Mathematical Statistics video series. Today I wanted you to do an interesting problem that is very subtle but really helps you think about distributions in applied work. So I'm going to consider this a foundational problem. So we still, haven't gotten into the kind of more mathy, I guess you could say, at least notation heavy problems, but we'll be getting there. I still want to work on just this problem for now. This is a really good problem. So suppose that there are n items arranged sequentially. Again, suppose sequentially and randomly. Again, suppose that each item is equally likely to be in any of the n spots. What is the expected number of searches from left to right until a desired item is found? Okay, so when you first see this problem, the story of this problem maps pretty closely to the story of a geometric random variable, right? Because you're saying, okay, how many times do I do something in sequence until I fail, or sorry, until I succeed. So how many failures do I have until I succeed, where a success is defined by choosing or finding the desired item. So this is not correct. It's not geometric, even though that's most people's intuition. And if that wasn't your intuition, great. And if it was, don't feel bad at all, because that is certainly a common mapping of this story to the geometric story. But one way to see this pretty easily is to always think, and I don't always do this myself, so practice do as I say, not as I do. But it's always good to think about, write down the support of the distribution. Okay, so what is the support of the distribution in this problem? What is the support? Well, we know that the item, this is the key point, is that we know that the item will be placed down in one of the n spots. So if we define our random variable, so let's define a random variable x to be the position of the desired item. What are the possible values that x can take on? Well, x is in the set 1 through n, right? Because since we put all the items down, it has to be in one of the positions that we put down. That's obvious, right? So by writing this down, we can immediately see that the geometric random variable is out, right? Because what is the support of the geometric random variable? It's 0 to infinity. So we immediately knocked off that distribution from our tree of possible modeling choices of this problem. Now we also see that each item is equally likely. Equally likely is a good indicator for uniform distribution problems. But even if you didn't notice that, a good thing to do would be to just start doing some experiments, right? So what is, for instance, let's evaluate what is the probability that x is equal to 1, right? So the desired item is in the first spot. So that happens with probability 1 over n, right? Because we had to choose the desired item, and there were n items to choose from, um, and so there's one choice you can make. Now, what about the probability that x is equal to 2? Well, what can happen that? How can x equal 2? Well, some other item, one of the n minus 1 items. Actually, let me start using fractions here because this is going to get messy without them. So we had to choose one of our n minus 1 items out of our n items. And then we had to choose one out of the n minus 1 items. Right? So this is the first item right here. Then we had to choose the second item as 1 over the n minus 1 remaining items. Okay, what does that simplify to? Well, that simplifies to 1 over n, right? Because we get this this cancellation here, this cross cancellation. And if you keep doing this out, that x is equal to 3. Again, we have, I don't like how LaTeX freaks out when you don't fill in the fractions. So let me just do it this way. We have n minus 1 choices for the item because we can't choose the desired item, n minus 2 because we can't choose the desired item and we already chose an item. And now we have one choice out of the remaining items, n minus 2 items, for picking the true desired item. Okay, so again we see this cross pattern here. N minus 1's canceling, n minus 2's canceling, and we see that this is equal to 1 over n, right? Okay, great. So proof by induction here, if we say that probability that x is equal to I, what is the probability that x is equal to I? Well, it's going to be some, n minus 1 over n times n minus 2 over n minus 1 dot 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 n minus I plus 1, right, over n minus I plus 1. See, because we have this 3 and this 2 here. So that's n minus 3 minus 1, otherwise known as n minus 3 plus 1, when you distribute the minus sign. So these are always going to be 1 over n, right? So that's another way you can immediately arrive at the uniform distribution, right? Because the probability of any, this is the uniform distribution. The probability of any value that x takes is equivalent. So now we can just appeal to the expected value, and we can say that the expected value of x is just the, is just n plus 1 by definition over 2. And that's the expected number of items searched. Cool. All right, see you next time.